All right, welcome everyone. So today we are continuing to talk about stratified samples. Based on what we're doing in class today, I recommend trying basically the first half of homework 5. Today I'll show you how to do some things in R to help with analyzing stratified samples. So if you're able, please bring your laptop on Thursday. That will make it a lot easier to analyze the data so you don't have to type it all into your calculator. All right, so let's start by briefly talking about graphing data from stratified samples. So if we have a quantitative variable that we're interested in studying, and we want to graph it across the different strata in our population, we can think of the different strata as being different values of a categorical variable that's dividing our population up into groups. So what are some strategies that you know about for graphing a quantitative and a categorical variable on the same graph? Or you could think of it as graphing a quantitative variable and showing how it differs between different groups. Leah?
I've done like quantitative where you change it to where you give it like 1 or 0.
Yeah, so we could put a threshold on the quantitative variable and then use a conditional bar graph. Sure, that'd work. What if we wanted to keep it as a quantitative variable? What graph did we see last time that we used for the iris data set? Anybody remember? It wasn't a bar chart, it was a histogram.
Right, okay.
Yeah. So we used a histogram with facets, where the facets refer to different subgraphs for the different groupings, the different strata. And the difference between a bar chart and a histogram is histograms are for quantitative variables, so where the order of the values on the x-axis is set, versus a bar chart, often the bars can be in alphabetical order or the order of frequency, or they can be rearranged. And that means that usually in a histogram, the bars will be right next to each other to indicate that one iris might have a petal length of 1.9 and another one has a petal length of 1.95. Those would be right next to each other. Versus in a bar graph, if we have a grouped categorical variable, then the iris is either red or it's yellow, but it's not somewhere in between. Another type of graph that you may have seen for graphing the relationship between a quantitative and categorical variable is a box plot. So these are nice for simplifying the comparison to really focus on sort of key points of the median, the first and third quartiles, and the extreme values, the maximum, the minimum, non-outliers, and then any outliers. And finally, a graph type that that you may not be as familiar with is a violin plot, which is similar to a box plot in showing a simplified view of the data, but it can show a bit more detail about the distribution. All right, so let's look at how to make all of these in R. So this is the graphing stratified samples, our Markdown document, so you can refer to this after class. And I'll start by loading my packages to make graphs and work with data frames. And then we saw last time, to make a histogram with facets, we're going to use the GF histogram function. And the argument inside there is squiggle and then the variable that we want on the x-axis. Yeah. Caitlin, sorry.
It's okay. What does the squiggle do?
Good question. So the squiggle is setting up a formula of like y squiggle x. And you'll see this if you do linear regression in R as well. That has the formula y squiggle x. So if there were something before the squiggle, that would be what we want graphed on the y-axis of our graph. But because a histogram, the y-axis is always the count of how many data points are in that range for our quantitative variable. We don't put anything before the squiggle. We just put the variable we want to graph after the squiggle. But in the next function, GF facet grid, so this is creating the different subplots, one for each species. Here we can put something before or after or both relative to the squiggle. So if we do it like this, we have species squiggle dot. That's going to put the species as the variable that controls the vertical arrangement of the graphs. So that looks like this graph that we saw last time. If we instead did nothing before the squiggle and species after the squiggle, now it's going to give us 3 graphs aligned horizontally, which sometimes is useful. For situations like this, I don't think it's as useful as the vertical alignment, because the vertical alignment lets you better compare how much overlap there is between the different species. And it is possible if we had another categorical variable in this data set, we could have something both before and after the squiggle, and then we would get a 2-dimensional grid of graphs. All right. For box plots, we are going to put something before and after the squiggle in the function gf underscore box plot. So the thing before the squiggle is going to be the quantitative variable that we want to graph. And the thing after the squiggle is going to be the grouping variable. So here's what that plot looks like. These are grouped by species. And just to refresh your memory, this horizontal line in the box plot is the median. The lower boundary of the box is the first quartile. So that's the data point where, or the value such that 25% of the data is below that and 75% is above. The top of the box is the third quartile. So 25% of the data is above it, 75% is below. And then the whiskers extend to the maximum and minimum non-outliers. So it looks like Virginica doesn't have any outliers for petal length. Versicolor has one outlier on the low end, and Setosa has 3 outliers, 2 below and 1 above. And this graph is showing us a similar finding to what we saw in the histogram last time, that because there's not much overlap between these boxes, that petal length is pretty different among these different species, and that there's a lot more variation from the maximum petal length to the minimum petal length overall compared to the amount of variation within each species. So that's, as we saw last time, telling us that stratified sampling is likely to reduce our sampling error, get us narrower confidence intervals. Questions about this? All right. And the third type of graph is a violin plot. So that uses the function gf_violin. And then the formula is the same as for a box plot. So the y variable is quantitative, squiggle, the x variable is the grouping variable. And I've added an optional argument here of draw_quantiles. And that's going to draw in the 25th percentile, 50th percentile, and 75th percentile. So the median, first quartile, and third quartile, like we had in the box plot. And I find that is helpful for being able to read the violin plot more easily. So here's what a violin plot looks like. So again, like the box plot, it's a pretty simplified view of the data, but it is giving us a little more detail as far as how the data are distributed. So the violin plot is wider in areas where more of the data lives. So here we can see that for Setosa, in the box plot, we saw that it was pretty tightly clustered around the median. Here we can see that it's clustered around the median in a way so that most of the distribution is really close to the median. It's not like it's all sort of evenly spread out throughout this range of this box. Questions about violin plots? All right. So one additional thing about graphing is sometimes you might be given a data set where instead of the groupings being given to you as words, like they are here, they might be given to you as numbers. So here I've just created a new variable called species num that equals 1 for Setosa, 2 for Versicolor, and 3 for Virginica. So same information, but now it's encoded as a number. And this can be a problem when you try to graph it. So I used the same structure of code as what we did earlier, just with species num instead of species as my grouping variable. And it gave me one big box plot instead of 3 grouped box plots. So that's because the box plot function is looking at the species num and thinking, oh, this is a quantitative variable. I don't know how to make a box plot for a quantitative variable. What do I do? So the solution to that is to use the factor function to tell R, treat this as a factor or categorical variable, not as a numeric variable. And when you do that, we get back the graph that we wanted, just labeled with the numbers that we assigned to the species rather than the species names. All right. So I wanted to come back to an example of estimating the mean from a stratified sample so that we can show you how to compute this using R, which is going to, in the long run, save you some time compared to doing it all in your calculator. So take a moment to read this problem and think about what formula you would use to solve it. So what formula do we want to use in order to solve this problem? Taylor?
Or was it like the 1 over n times the summation of n sub I and then y bar sub I?
Yeah. So thinking about the data in this table, we want to take each of the n sub i's, so the population size of that stratum, times each of the y bar sub i's. Add those up and then divide by 593, the total population size. So in order to do this in R, here's what this can look like. We can use the lowercase c function to create a vector to store each of these data values from the means, and similarly to store each of the strata population sizes. And here I've called these my means and my n. There's nothing particular special about those variable names. I just like to try to keep my variable names informative about what's in them and not duplicate the names of any functions. So I'm not using just the word mean because that's also the name of a function in R, and it can be confusing to have a variable with the same name as a function. And then we can take the sum of my n and verify that, yes, that is 593. So that's a check that, yes, we typed things in correctly, that this matches what we were told the total population size was. And then, if we take my means times my n, that's going to pairwise multiply each element of my means by the corresponding element of my n. So if we then take the sum of that and divide by 593, that gives us our estimated mean from the stratified sample. All right, what if we wanted to find a 95% confidence interval for mu? Then what formula would we need? Well, our 95% confidence interval, like it has for all the other parameters we've estimated in this class, is going to be our point estimate, so y bar sub st, plus and minus 2 times an estimate of the standard deviation of our point estimator. How are we going to find the standard deviation?
Yeah, so they square root of variance.
Yeah, we'll take the square root of the variance, which has kind of a complicated formula for a stratified sample. So here's how we can compute that in R. So I'm using the same values of my n from the previous slide. Now I also have my little n for the sample sizes from each stratum, and my SD for the standard deviations from each stratum. And then you can look at each piece of what we're doing here. We have my big N squared, so that's the n sub I squared, times my big N minus my little n, in parentheses, divided by my big N. So that's our finite population correction factor. And then times my SD squared, so the square of the standard deviation, so that's the variance within each stratum, divided by my little n. So we're computing that for each stratum, and then taking the sum across all the strata. And then dividing by 593 squared. So that's our variance. So then our confidence interval will be our y bar sub st that we found on the previous slide, 5.25, plus or minus 2 times the square root of the variance. Are there questions about this? All right. So I should mention that this C function is a good way to get the data in if you have it like in a table. But if you've already read the individual data points from the sample into R, and you're calculating the mean and standard deviation, then you don't necessarily have to retype them with this C function. Ted asked a great question about this in office hours today, so there's a recording of that on Canvas. So check that out if you want to be able to do these calculations in R without having to retype something that you've already used R to calculate. All right. I wanted to briefly mention how to estimate the population total, tau. So we talked about this for a simple random sample. And the formula for this is going to be simply the total population size n times y bar sub st, so times the sample mean as estimated from stratified sampling. So this is the same formula as we use to estimate mu, just we're not dividing by big N at the end. And you'll recall that when we want to find the variance of big N times a random variable, we can pull the constant, big N, outside the variance, and then it becomes squared. So we really just end up with an estimate of the variance, or our estimator for tau, of the same thing that we had for our variance for y bar sub st, just times n squared. All right, let's get back. So now let's talk about choosing a sample size for stratified sampling. In order to do this, we need one piece of notation, and that is we'll use A sub I for the allocation. That is the proportion of the sample that belongs to stratum I. So in other words, n sub I, the number of observations in our sample that are from stratum I, is equal to our total sample size little n times the allocation A sub I. All right, so just like when we talked about this for a simple random sample, we might want a margin of error for our confidence intervals of b or less. So that's our goal for our level of precision that we want in our estimate. So that means we want 2 times the square root of the variance of y bar sub st to be less than or equal to b. So we can multiply both sides of that by 2, or divide both sides of that by 2, sorry, and then square both sides. So we want the variance to be less than or equal to b squared over 4. So this part is the same as what we did for simple random samples. And then we can go ahead and plug in our formula for the variance of y bar sub st. Now, we'd like to have this so that we can compute our overall sample size little n, rather than having to separately compute each of the n sub i's. So let's go ahead and substitute in n times a sub I for each of the little n sub i's. So that ends up looking like this. So now our goal is going to be to try to simplify this inequality and try to get n by itself on one side of the inequality. So we can start by just multiplying both sides by n squared, big N squared. And then let's swap the denominators of these two factors that are inside the summation. So then we can simplify our middle factor here by dividing this into two fractions. So we have n over big N sub I over little n times a sub I minus 1. So this is good because now we just have little n in one place on the left-hand side. So we'll be better able to isolate little n. All right. Next, we multiply our two factors together. So we have sum of big N sub I squared times the quantity big N sub I times s sub I squared over little n times a sub I times big N sub I minus s sub I squared over big N sub I. All right. The big N's cancel. And we're multiplying this n sub I squared into the parentheses. So that gets the n sub I out of the denominator in the second term. And now, what we have here is a sum of a bunch of copies of things that involve this subtraction. Well, we can split that apart into the sum of n sub I squared over na times s sub I squared minus the sum of big N sub I times s sub I squared. So try finishing the problem from here. Try isolating little n on one side of the inequality. So we can start by adding the sum of big N times S squared to both sides of the inequality. And then we can pull the 1 over little n outside of the summation, because that doesn't depend on I. So we can factor that out. And then we're trying to get n by itself. So if we multiply both sides by n and divide both sides by all of what's currently on the right-hand side of the inequality, we get little n needs to be greater than or equal to the sum of big N squared times S squared over A sub I, all over big N squared times B squared over 4, plus the sum of big N times S squared. Questions about this? Dan, any questions? All good? All right. The sample size to estimate the population total tau within a margin of error B is exactly the same, except for we have B squared over 4 instead of N, what was it? N squared times B squared over 4. So let's try using this. So suppose that this is our preliminary data, maybe from last year, on the hours that Math 246 students study per week. And we plan to take a new sample where a quarter of the sample is going to be from each class. And we want to estimate the mean hours that people spend on homework in Math 246 with a margin of error of 0.3. Try finding the sample size that we're going to need. So the 1/4 of our sample is telling you that A sub I equals 1/4 for all 4 of these strata. Here are some values of some preliminary computations I did in R. So the sum of n times s squared is 1502.461, and the sum of n squared, or big N sub I squared times s squared over 1/4 is 819,142. So then if we plug those into our formula, those are going in the numerator and sort of the second part of the denominator. And we end up with, we need a sample size greater than or equal to 87.008. So if we round that up to 88, then we need a total sample size of 88 with 1/4 of the sample coming from each of the 4 class years. So we could gather 22 people from each class year to get a margin of error of 0.3. Questions about this? One important question would be, can we do any better by changing allocations? So if instead of using 1/4 of our sample from each class year, maybe we could get by with a smaller sample size by using some different proportions. So that's what we'll start with on Thursday. I'll see you then.